Cool. All right, we're just gonna get started with the demo for this week, and hopefully people will start trickling in. So first and foremost, today the topic is just going to be fusion joints, and basically how to model fusion joints, especially with slightly more complicated things going on, and how to make things look somewhat realistic. So we're going to talk about some techniques to do that, some ways that Fusion sort of helps you out in figuring out how things are going to work together. And then I'm going to show you the actual model that we built and also some tips for how to build out models so they're easy to edit and extrude and mess around with, especially in this constraint. So without further ado, we're going to jump into the software. So right here you can see this actually looks nothing like what we're talking about today, which is the first ever circular saw. The first circular saw was an invention of a woman. She was a Quaker, so she didn't patent it because that wasn't the way, apparently. So it was later patented by a man, but doesn't change the history. And the reason we're doing this is because obviously back before motors existed and were commonplace and could drive things like this, like they do now, we needed another way, and we needed a way that was more manual, but also still easy. So what you see in a lot of older machines, like old sewing machines or things like this circular saw, is a joint system called a treadle. And the treadle basically allows you to cause circular motion with something like a foot pedal. And that makes it easier to do work like this for a continuous period of time, like they would if you were operating on a sewing machine or a circular saw or something like that. Because obviously it's a foot pedal, so you're not sitting there cranking, you're just tapping your foot, which is a lot easier for people to do over a long period of time. So something that's might be interesting is, as you can see, this is a 2D geometry, but it's not one sketch. This is actually this is 4 different sketches, really. 1, 2, 3, yeah, four different sketches. And they're jointed together as if they were actual components, and they are components, but they're not extruded. And that's something that you can do in Fusion. That's very helpful for just really, really simplifying a design, especially one that requires movement, that you want to simulate the movement ahead of time. You can join together 2D sketches like this and see how something is going to go together and work together before you get into the complexity of a 3D geometry, and that's really helpful. This is a simplistic motion, but we still need 2, 3, 4, 5 different joints and a motion link to achieve what we're trying to do, and we need at least 4. 2 of these are technically unnecessary, but work because of what we're building today. So first and foremost, I can kind of show you what the end goal here is by animating the model, and you can see this is representative of the foot pedal right here. This is a linkage going from the foot pedal to the main wheel, the driving wheel. And this linkage goes to the top wheel. And this guy is what the saw or whatever it is that's rotating is attached to. Obviously, it's actually, in this case, it's exactly half the size of the larger wheel. So it's going twice the speed, which obviously is useful for something like a saw. And really all we had to do to achieve this was we set up our initial sketch and created that as a component, as if we were just doing any other regular Fusion, right? We're starting with a component and then we're sketching onto the component. But instead of our next step being an extrusion, like you might expect, we're just going to make another component, and that's going to be our pedal. And then we're going to create a sketch for that, and then create yet another component, which acts as our linkage. And that is really just going into the sketch tool and using this guy right here, the slot command, which can make things a lot faster. And then we're going to just joint these things together. We're not even going to worry about the smaller wheel because it's pretty simple, but it's, potentially more complicated than we need it to be. So when you're doing joints, what you really want to try to do is a top-down approach. So the first and foremost, I want this big wheel to spin around its axis. So that's the first thing I'm going to do. What I'm going to do for this entire assembly is not a conventional joint. I think that's what most people use, probably because it's just right here and they think that's kind of the default. What we're actually going to use is an as-built joint. And the reason we're doing that is because we're sketching everything and we're creating components where we want them to ultimately end up. We don't want them to move. So what an as-built joint does is it establishes the relationship of that object based off of where it is now. So this first joint is a as-built joint that's created in relationship with the very top layer of our tree. And what that's doing is establishing this rotational revolutionary relationship between the center axis of this component, which is just a sketch, but still a component, and the origin planes of the entire model itself. And that really kind of grounds the sketch while allowing it to move around. And so if all of these other sketches are based off of this one to some extent, which they are, then all of these sketches will also be grounded to the origin planes of our actual design, which is exactly what we want to do. From here on out, the order does not really matter on what we're doing. So what we're going to do first is do this pivot point. It's just another revolutionary point. And we're going to go from there. So not anything too complicated. We're doing yet another revolution around this off-axis pivot, which is what is allowing us to get that torque. The linkage to the foot pedal. And then we're just going to create a new component, which is going to pop up top here. And this is our smaller wheel. Again, not necessary, but it's good for visualization. That's also going to get a revolution because this is independent. It's going to revolve in relation to our topmost layer yet again. And then the last thing we're going to do is just link those two motions. You'll notice that these aren't even physically connected, and they don't have to be. All I have to say is that I want you to rotate when you rotate in that order. Essentially, all I have to do is select the driving joint first, and then the following joint, and then establish what kind of relationship they have, which, going back to last week, we can do parametrically if we so desire. So that's 2D, and that's really cool, and it really simplifies our design. The other thing that starting with this 2D allows me to do is really play around with the driving dimensions of this pedal, for example, and figure out, okay, what's actually going to work? Because obviously this has a linkage in it, and it has multiple components that are interacting with each other. So there is that risk that something is going to lock up if your dimensions aren't right. And that certainly happened to me when I was designing this. I had to play around with these dimensions to make sure that, at this most extreme point, this whole joint system wasn't going to lock up. The good thing is that Fusion will pretty much show you when something's locking up by stopping and showing you that it can't get past that point, which is why it's useful to simulate these joints. So this is all fine and dandy, but we do want to have something that's a little bit more three-dimensional once we figure all that out. So then we jump on to our next sketch. All of these are essentially more or less the same. The only difference is there is a fixed joint on this bottom pin. It is a fixed pin. And the only reason we have that is because in our 2D layout, this is just a point that's connected directly to this pedal. In our 3D layout, this is an actual separate component. We didn't have this component in our 2D layout. So we have to let Fusion know that, like, hey, this doesn't move. And if you had this in real life, it also wouldn't move. Other than that, pretty much everything from the dimensions to the lengths of things and all of that is very similar, if not the same. You'll notice that this linkage is in the middle instead of on the very end. And that's more so to simulate what we would typically see in an assembly like this in real life. Something that I just really quickly want to draw attention to is the method that I used to CAD this. I very briefly mentioned this concept at the beginning in the CAD demo last week. But it is just immensely useful to sketch things and CAD things on a plane and then extrude them both ways. So you're basically working off of a middle plane. And this design is a really good example of why that's important. So I started out with a new component, which was my main wheel, just like in the last sketch. What you'll notice about this sketch, I'm starting it on pretty much the vertical plane. And what I do next is I extrude it, but the way that I extrude it is rather than going from one end out, I'm going to extrude this both ways, symmetrically. That way, when I go in and I want to make this grooved feature on here for something like a van belt or, whatever is going to drive the small wheel to go as well, I can sketch that off of the mid plane again, the origin plane again. And then I can just extrude that both ways as well. And that way I have a geometry that's perfectly centered on my original geometry, and I don't have to offset it or anything like that. So then if this geometry changes for some reason, like if I make it thicker or something like that, if I move it around, nothing's going to happen to this centered geometry here. The other thing is then when I go to line up these two, the large wheel and the small wheel, I can just continue to sketch everything off of that XY origin plane. And it's just going to be in the right spot. And obviously it'll also be locked onto that origin plane. It's not going to move in either direction unless I move it, which it won't happen obviously because I'm going to lock it in with my joints later on. And so everything just sort of falls into place when you sketch on the center line and extrude symmetrically both ways, especially if you have like very symmetric geometry like this, which we often see because we're humans and we love symmetry if we can get it. So you'll see I actually make the small wheel next, and I'm doing the exact same thing, making that on the center plane, and then making that same sized groove. And then I'm going to make all of my pedal geometry. Functionally still, you can see I'm still creating the sketch on that center line and extruding both ways. And that way I know, right, when I go to one of these side views, everything is perfectly aligned and continues to be aligned as I add things in, and they're going to stay that way. And it's just a more consistent way to CAD things if you can. I like to mention that because I think it flies in the face of like our traditional CADing methods. I think the vast majority of us, especially when we start off doing CAD, we like to just sketch things on a plane and extrude it up because that's usually the first option you get. But just to draw it to your attention, that is certainly not the only way to CAD something, and it's not necessarily the best way to CAD something so that the design will last a long time and will be able to be edited and altered easily. There are also a lot of benefits to doing this from a machining perspective, which we won't do too much. So yeah, I'm just doing the rest of the geometry. The other cool thing about doing things on a central plane is for this linkage. For example, instead of having to grab this and offset it a certain way, all I need to do is mirror this across the central origin plane. And it's just going to exist on the other side now, which is very helpful and, makes the process just a little bit faster. All of these joints then are exactly the same as what they were in the 2D. The 2D practice run, if you will. We're doing the main rotational joint on the big wheel that's jointed to the top of our component tree. And then we're sort of backtracking through the rest of the design so that everything that needs to rotate rotates and everything that shouldn't move doesn't move. And then the last thing we're doing is just linking those two joints. And really, I think sometimes we think, oh, we can link all of these joints together. Um, but it's best to avoid adding a bunch of linkages if you can. The goal with all of this is to keep things as simple as physically possible. Because the more, obviously, the more complicated that this gets, the more, the higher the likelihood that something catastrophic will happen and you won't be able to figure out how to put it back together again. Which has also happened to me, where you just have something acting really, really strangely, and you don't know how to fix it anymore. So you just delete all your joints and try again, and then it happens again, which isn't super fun. So let's avoid that if we can by keeping things simple. And then I can go ahead and animate. I can also animate this joint if I want to. That's why we want to name our joints, right? Is so that we know what they're actually doing. Naming things like joints can be just as important as naming components, not only for you, but obviously, you know, CAD is a collaborative thing for the most part. So when someone else goes into my model, I want them to know, like, okay, why is this there? So by naming these as well, people can see, okay, this joint does this joint does this, yada, yada. So if something happens with the overall design and one of these joints breaks for some reason, then I can go back and I know what to fix because they're all labeled. If that isn't done, or you don't really know what a joint is supposed to do, you can also always animate that joint and it'll show you what it's controlling. The other thing that we don't utilize here, but we could if we really wanted to, is, say, for example, we wanted the angle of this pedal to be limited. It already is by the natural mechanism that is occurring here because everything is all put together. But say it isn't, or, you know, CAD isn't super, super smart yet, so it doesn't necessarily know if something is interfering unless you go in and you do extra stuff. So one of the things you can do to limit how far one of these can go is you can just go in, or we'll do this guy. You can go in. Actually, I like doing this here. Yeah. Edit joint limits. I couldn't do it on the rigid fixed joint because obviously it doesn't move. So the joint limits go to infinity, if you will. It can't go anywhere. But I can do it on anything that is not a fixed joint. So something that has some amount of movement to it. So if I were to do this, I can limit how much it can rotate, give it a minimum and a maximum amount of rotation. And the other thing that's nice is I can set a rest position. So like this is its natural state. Or I can flip the animation if, you know, that's the direction that it will generally be going. So those are all useful tools that might help in animating joints and all of that good stuff. And if I go in, okay, and I animate my model, then this all works together. It works slightly differently because, like I said, I was playing around with it, so the dimensions are different, especially this middle axis dimension is what changes it up. But if I wanted this to behave differently, the way I have it catted is you just have to change the location of this pin right here, up, down, or laterally, and everything will edit. And that's ideal if you can afford to. Sometimes complex mechanisms, you can't really do that, but if you can, you probably should because it makes your life easier. Because when you're trying to figure out why something is broken or won't work, it's easiest to just be able to change one or two dimensions. And just make it happen. And obviously I didn't do any calculations to make this work necessarily. I just started in the 2D layout, figured out what was going to work, what wasn't going to work. And then I translated that into an actual 3D model with the same relationships. So yeah, that is all I have. If there are any questions, I can field them. Otherwise, that's the CAD demo this week. And we'll close it